December 16th, 1944. The Schnee Eifel, Belgium. Oberst Friedrich August von der Heyde crouched behind a snow-laden pine tree as American artillery shells screamed overhead in the pre-dawn darkness, their distinctive whistling growing louder with each salvo. As commander of Kampfgruppe von der Heyde, a paratrooper battle group spearheading the northern thrust of Operation Wacht, and Rhein Hitler's desperate gamble to split Allied forces and recapture Antwerp, he had experienced 4 years of Allied bombardments from North Africa to Normandy. But something was different about these explosions. Terribly, impossibly different. Instead of the familiar pattern of shells detonating when they struck earth or trees, creating localized damage that his veteran paratroopers could survive in foxholes and trenches, these projectiles were exploding 30 feet above the forest canopy in perfect, synchronized airbursts that showered deadly shrapnel fragments across hundreds of yards of terrain. His men, who had endured the inferno of Monte Cassino and the hell of the Normandy hedgerows, were screaming in ways he had never heard before, not the sharp cries of men struck by bullets or the agonized shouts of soldiers caught in normal artillery barrages, but the bewildered wails of troops experiencing something beyond their comprehension of warfare. As Hyde peered through the swirling snow and smoke, watching entire squads of his elite Fallschirmjäger disappearing under the precisely timed aerial explosions, he realized with growing horror that the Americans had somehow mastered the mathematics of death itself, transforming artillery from a weapon of area denial into an instrument of surgical precision that could reach his soldiers regardless of cover, concealment, or terrain. What von der Heyde could not comprehend, as he watched his battle-hardened paratroopers being systematically destroyed by explosions that seemed to possess supernatural timing and placement, was that he was witnessing the first large-scale deployment of the most closely guarded technological secret of World War II, the proximity fuse, designated VT, variable time, by American forces. This wasn't simply improved artillery, it was the weaponization of advanced electronics, radar technology, and mass production techniques that represented a quantum leap in the science of killing. Each shell bursting above his men contained a miniaturized radar transmitter and receiver, vacuum tubes smaller than a thumb, and electronic circuits that could calculate optimal detonation altitude while spinning at 500 revolutions per second and withstanding acceleration forces exceeding 20,000 times the force of gravity. The Americans hadn't just built a better fuse, they had created a thinking projectile that could analyze terrain, adjust for target density, and execute perfect airbursts with mathematical precision that rendered traditional defensive tactics obsolete. The systematic destruction of Kampfgruppe von der Heyde represented more than tactical innovation. It was the introduction of electronic warfare to the battlefield, the marriage of Silicon Valley engineering with Detroit mass production that would transform every future conflict and establish American technological superiority for generations to come. The scientific foundation of the proximity fuse represented perhaps the most remarkable marriage of theoretical physics and practical engineering achieved during the war years. Developed at Johns Hopkins Applied Physics Laboratory under the direction of Merle Tuve, the VT fuse incorporated technological innovations that had required the coordinated efforts of 300 engineers, 1,000 technicians, and partnerships with 35 American universities conducting classified research programs. The basic physics involved transmitting radio waves at 180 to 220 MHz from a miniature antenna embedded in the nose of an artillery shell, then measuring the Doppler shift in reflected signals to calculate precise distance to target. When the return signal indicated optimal burst height, typically 30 to 50 feet above ground, for maximum shrapnel dispersion, the electronic circuit triggered detonation through a system that functioned reliably, despite the claste projectile's rotation, the intense heat and shock of firing, and the electromagnetic interference common to battlefields. Each proximity fuse contained 23 separate components, including 5 vacuum tubes manufactured to tolerances measured in thousandths of an inch, a battery capable of delivering 22.5 volts after withstanding launch accelerations that would destroy conventional electronics, and a safety mechanism that prevented premature detonation until the shell had traveled at least 400 yards from the gun. The engineering challenges were staggering. creating electronics that could survive being shot from a cannon, while remaining sensitive enough to detect ground reflection at precisely the right moment for maximum lethality. The 105 mm high explosive shell, equipped with a VT fuse, could produce a casualty radius of 60 yards compared to 10 yards for the same projectile, with a contact fuse, a six-fold increase in effective killing area that multiplied artillery effectiveness by factors that German defensive doctrine had never contemplated. The mass production of proximity fuses revealed an industrial achievement that paralleled the Manhattan Project in complexity, while exceeding it in scale and immediate battlefield impact. By December 1944, American factories were producing 40,000 VT fuses per day through a manufacturing network that included Western Electric, Eastman Kodak, Crosley Corporation, and dozens of smaller contractors specializing in precision electronics. The Crosley plant in Cincinnati alone employed 8,500 workers, operating in 3 shifts around the clock, assembling the miniature vacuum tubes that formed the heart of each fuse's radar system. These weren't the large, fragile tubes found in household radios, but rugged components designed to function after experiencing launch forces equivalent to being dropped from a 20-story building. The Western Electric facility in Kearney, New Jersey, manufactured the electronic circuits using assembly line techniques adapted from telephone switching equipment, producing components with reliability standards that exceeded anything previously achieved in consumer electronics. Each production line required quality control procedures that tested random samples by actually firing them from artillery pieces at Aberdeen Proving Ground in Maryland, ensuring that shells reaching frontline units would function exactly as designed when American gunners needed maximum effectiveness. The batteries powering each fuse represented their own technological marvel silver-zinc cells that could deliver full voltage after months of storage, while occupying space smaller than a cigarette pack. By the time of the Bulge offensive, American factories had produced over 1.2 million proximity fuses, with production capacity sufficient to equip every artillery shell fired by American forces if tactical requirements demanded such deployment. The tactical implementation of proximity fuses during the Battle of the Bulge demonstrated how technological superiority could compensate for numerical disadvantage and strategic surprise. German forces launching Wacht am Rhein possessed initial advantages in men, tanks, and artillery. Field Marshal Walter Model's Army Group B deployed 200,000 troops, 600 tanks, and 1,900 artillery pieces against thinly held American positions in the Ardennes forest. The German plan depended on achieving breakthrough before American reinforcements could arrive, exploiting winter weather that grounded Allied air power while advancing through terrain that channeled attacking forces into predictable corridors. What German planners hadn't anticipated was facing defensive artillery systems that could achieve devastating effectiveness, regardless of weather, visibility, or terrain advantages. The American 106th Infantry Division, despite being overrun in the initial assault, had deployed its 105 mm howitzers with proximity fuses that inflicted casualties far exceeding what German assault troops expected from defensive artillery. The 333rd Field Artillery Battalion, supporting the embattled 101st Airborne Division at Bastogne, discovered that VT fuses transformed their 105 mm guns into area denial weapons that could halt German infantry attacks across entire grid squares. Each battery of 4 howitzers, firing at maximum rate with proximity fuses, could deliver 240 airbursts per minute across a frontage of 1,000 yards, creating a steel umbrella of shrapnel that made coordinated infantry assault virtually impossible. German forces that had successfully attacked across similar terrain in 1940 and 1941 discovered that technological evolution had fundamentally altered the mathematics of offensive warfare. The psychological impact of proximity fuses on German troops exceeded their tactical effectiveness, creating a form of technological terror that undermined morale and unit cohesion throughout the offensive. Wehrmacht veterans who had survived the Eastern Front, Normandy, and years of Allied bombing reported that proximity fuse artillery produced a unique form of battlefield stress. The knowledge that no defensive position provided safety from explosions that seemed to possess supernatural intelligence. Traditional artillery could be survived through proper field fortifications, movement techniques, and experience reading the sounds of incoming shells. Proximity fuses eliminated these survival skills by creating airbursts that showered shrapnel into trenches, behind cover, and across terrain that should have provided protection. SS Oberfuhrer Wilhelm Mohnke, commanding the 1st SS Panzer Division, Leibstandarte Adolf Hitler, during the northern thrust toward Antwerp, documented the psychological effects in his combat reports. American artillery has acquired an almost mystical accuracy that affects soldier morale. Our men report that shells explode at precisely the right height to cause maximum casualties, regardless of cover or concealment. Experienced NCOs who have survived years of combat express superstitious fear about American artillery capabilities. Unit cohesion suffers when soldiers cannot trust their defensive training and experience. The 12th SS Panzer Division, Hitlerjugend, composed of fanatical young volunteers who had fought with desperate courage in Normandy, began showing signs of artillery neurosis after 48 hours of exposure to proximity fuse bombardments. German medical officers reported unprecedented numbers of combat stress casualties among troops who had previously demonstrated exceptional resilience under conventional artillery fire. The technical sophistication of the VT fuse represented a convergence of multiple advanced technologies that American industry had developed independently for civilian applications before the war. The miniature vacuum tubes essential for radar operation had evolved from research conducted by Bell Telephone Laboratories for long-distance communications, while the precision manufacturing techniques came from the radio industry's mass production of consumer electronics. The Doppler radar principles were derived from research at the Massachusetts Institute of Technology and the Naval Research Laboratory, where scientists had been investigating aircraft detection and navigation systems since the late 1930s. The rugged battery technology came from developments in hearing aids and portable radios, scaled up through industrial processes that could produce millions of units with consistent performance characteristics. Most remarkably, the electronic circuits incorporated feedback control systems that automatically compensated for variations in shell trajectory, target density, and atmospheric conditions. Primitive analog computers that performed calculations while spinning through the air at artillery velocities. The proximity fuse represented the first practical application of what would later be called smart weapons, projectiles capable of making autonomous decisions about when and where to detonate for maximum effectiveness. German scientists, despite their theoretical knowledge of radar and electronics, lacked the industrial infrastructure necessary to manufacture such complex devices in military quantities while maintaining the reliability standards required for battlefield deployment. The intelligence failure that prevented German forces from developing countermeasures to proximity fuses demonstrated the effectiveness of American operational security, combined with deliberate misdirection campaigns. Despite capturing thousands of unexploded American shells during the Normandy campaign and subsequent fighting, German technical intelligence services had failed to recognize the revolutionary nature of VT fuse technology. Captured fuses were analyzed by teams at the German Army's weapons testing office at Kummersdorf, but investigators assumed they were examining conventional time fuses with unusually complex mechanisms. The electronic components were so miniaturized and ruggedly constructed that German engineers couldn't determine their function without sophisticated testing equipment that had been destroyed by Allied bombing. Moreover, American forces had implemented strict security protocols that prevented proximity fuses from being used in situations where duds might be recovered and analyzed. Early deployments were limited to naval anti-aircraft systems over water, where failed shells would sink rather than fall into enemy hands. The first land-based use of VT fuses occurred during the Battle of the Bulge, specifically because American commanders calculated that winter conditions and rapid tactical movement would prevent systematic German technical intelligence gathering. Even when German engineers finally recognized that American shells contained radar systems, they lacked the industrial capacity to develop countermeasures or produce competing technology while fighting a defensive war against overwhelming Allied material superiority. The mathematical precision of proximity fuse effectiveness transformed artillery from an area weapon into a surgical instrument capable of engaging specific tactical targets with unprecedented accuracy. Traditional artillery doctrine required extensive ammunition expenditure to achieve desired effects. A typical battery might fire 200 rounds to neutralize a company-sized defensive position, with most shells providing minimal contribution to the tactical objective. Proximity fuses reduced ammunition requirements by 75%, while increasing casualty production by 300%, creating efficiency gains that multiplied the effective firepower of American artillery units. The 155 mm long-tom artillery pieces supporting the defense of Bastogne could engage German troop concentrations at ranges exceeding 14 miles with VT-fused shells that produced reliable airbursts regardless of terrain or weather conditions. Battery commanders reported that single proximity fuse missions could accomplish tactical objectives that previously required sustained bombardments lasting hours. The mathematical advantage compounded across entire sectors. The 8th Corps Artillery, supporting American forces along the Bulge perimeter, achieved ammunition savings of 40% while increasing effective firepower by 250% through systematic VT fuse deployment. German forces attacking American positions discovered that defensive artillery had achieved levels of effectiveness that made traditional assault tactics, suicidal breakthrough operations that had succeeded against Soviet and British forces, became impossible when facing American artillery systems equipped with proximity fuses. The logistical implications of proximity fuse deployment revealed the depth of American industrial planning and the sophistication of military supply chains that could deliver advanced technology to frontline units under combat conditions. Each VT fuse cost $18 to manufacture compared to $0.50 for conventional contact fuses, but the tactical effectiveness justified the expenditure through reduced ammunition consumption and increased mission success rates. Special transport and storage requirements meant that proximity fuses required climate-controlled warehouses, careful handling procedures, and technical personnel trained in electronic maintenance logistics challenges that American forces met through systematic planning and resource allocation. The European theater of operations maintained VT fuse stockpiles at 47 ammunition depots, with distribution networks that could deliver specialized munitions to any artillery unit within 48 hours of request. Quality control procedures included random testing of production batches at firing ranges established specifically for proximity fuse verification, ensuring that shells reaching combat units met performance standards. The technical support infrastructure included mobile electronics workshops that could diagnose and repair malfunctioning fuses, plus training programs that educated artillery crews in proper handling and deployment procedures. German forces, by contrast, struggled to maintain adequate supplies of conventional ammunition while dealing with transportation networks disrupted by Allied bombing and fuel shortages that limited distribution capability. The evolution of American proximity fuse technology during the war demonstrated how industrial research and development could accelerate innovation through systematic application of resources and talent. The original VT fuse design, tested in 1942, weighed 2.1 pounds and required a 3-second arming delay that limited its tactical applications. By 1944, improved models weighed 1.3 pounds with a 1.5-second arming time and enhanced sensitivity that could detect individual vehicles or small troop concentrations. The Mark 53 proximity fuse, entering production during the Battle of the Bulge, incorporated waterproof sealing that allowed storage in field conditions for 6 months without degradation, plus improved circuitry that functioned reliably at temperatures ranging from -40 to +160 degrees Fahrenheit. Research teams at Johns Hopkins Applied Physics Laboratory were simultaneously developing VT fuses for 76 mm tank guns, 40 mm anti-aircraft weapons, and even small arms ammunition technological diversification that would have equipped American forces with proximity fuses across the entire spectrum of tactical weapons. The manufacturing infrastructure established for artillery fuses provided the foundation for post-war electronics industries that would dominate global markets in television, radio, and eventually computer systems. American engineers weren't just building better weapons, they were creating technological capabilities that would define industrial leadership for decades to come. By December 22, 1944, 6 days after the German offensive began, the cumulative impact of proximity fuse artillery had fundamentally altered the tactical balance of the Battle of the Bulge in ways that German commanders struggled to comprehend. The 2nd SS Panzer Division Das Reich, attempting to capture the vital road junction at Baraque de Freture, discovered that American defensive positions could engage attacking forces with artillery effectiveness that exceeded anything previously experienced on the Western Front. Each German assault faced artillery barrages that seemed to anticipate troop movements, concentrate on specific tactical targets, and achieve devastating effects with minimal ammunition expenditure. The 116th Panzer Division, advancing toward the Meuse River crossings, reported that American artillery could halt regiment-sized attacks with battery-level fires that produced casualty rates comparable to division-scale bombardments using conventional weapons. German medical units treating proximity fuse casualties noted wound patterns that differed significantly from standard artillery injuries, multiple penetrating fragments distributed across larger areas of the body, suggesting airbursts optimized for anti-personnel effectiveness. The 12th Volksgrenadier Division, composed primarily of older reservists and recent conscripts, suffered psychological breakdown after 72 hours of exposure to proximity fuse bombardments that killed experienced soldiers who should have survived conventional artillery through proper fieldcraft and defensive procedures. The strategic implications of proximity fuse deployment extended beyond immediate tactical advantages to demonstrate American technological superiority that would influence post-war military development worldwide. Soviet observers, despite being Allied partners, requested detailed technical information about VT fuses through diplomatic channels, recognizing that American electronics represented capabilities that the Red Army lacked despite its overwhelming advantages in conventional weapons production. British intelligence services, possessing their own advanced radar and electronics programs, acknowledged that American proximity fuse technology exceeded anything developed in European laboratories, while simultaneously achieving mass production levels that made widespread battlefield deployment possible. The successful marriage of advanced science with industrial manufacturing demonstrated American advantages that transcended simple production capacity, the ability to transform theoretical research into practical weapons systems delivered to frontline troops in quantities sufficient to influence major campaigns. German technical intelligence reports, when they finally recognized the nature of American proximity fuse technology, estimated that duplicating such capabilities would require 18 months of development time, plus industrial resources, equivalent to their entire electronics production capacity. The technological gap had become insurmountable for nations fighting defensive wars with declining industrial capacity against enemies possessing unlimited research and development resources. The human dimension of proximity fuse effectiveness became apparent through individual unit histories that documented the systematic destruction of German assault formations during the critical phases of the Bulge offensive. The 394th Infantry Regiment, defending positions near the village of Lochheimergraben, reported that a single battery of 105 mm howitzers equipped with VT fuses could halt battalion-sized German attacks that had previously required coordinated fires from multiple artillery battalions using conventional ammunition. Sergeant Robert Hayes of the 333rd Field Artillery Battalion, supporting the encircled 101st Airborne Division at Bastogne, documented the psychological impact of proximity fuses on German prisoners. Captured SS troops consistently ask about our magic shells that explode in the air. They described the sound as different from regular artillery, a sharper crack followed by a rustling noise as shrapnel falls through tree branches. Veteran NCOs who survived years of fighting on the Eastern Front expressed genuine fear about our artillery capabilities. They understand that their defensive training has become obsolete against weapons that can reach them regardless of cover or concealment. The effectiveness transcended simple casualty, statistics, proximity, fuses, were systematically destroying German unit cohesion, by eliminating the defensive techniques that had allowed experienced soldiers to survive conventional artillery bombardments throughout the war. The technical complexity of proximity fuse manufacturing revealed the depth of American industrial capabilities that German planners had consistently underestimated throughout the war. Each VT fuse required precision assembly of components manufactured to tolerances exceeding aircraft engine standards, vacuum tubes with filaments thinner than human hair, capacitors capable of storing electrical charge while withstanding artillery acceleration, and antenna systems that could transmit radio signals while spinning at hundreds of revolutions per second. The Western Electric facility in Burlington, North Carolina, employed 1,200 workers operating specialized machinery that could wind radio coils with wire measured in thousandths of an inch while maintaining electrical characteristics within 2% of design specifications. The Eastman Kodak plant in Rochester, New York, contributed precision optics and mechanical timing systems that required manufacturing accuracy comparable to camera equipment, while possessing ruggedness sufficient for military deployment. The industrial network supporting proximity fuse production included 127 subcontractors, providing everything from specialized metals to precision ground glass components, coordinated through supply chains that delivered materials with reliability that German industries couldn't match during wartime conditions. Quality control procedures required testing random samples from each production batch by actually firing them from artillery pieces, creating feedback loops that continuously improved manufacturing processes while ensuring battlefield reliability. The tactical evolution of proximity fuse employment demonstrated how technological advantages could be rapidly integrated into existing military systems through training programs and doctrinal adaptation that reflected American organizational flexibility. Artillery officers at the Command and General Staff College at Fort Leavenworth developed new firing techniques that maximized VT fuse effectiveness against specific target types, concentrated airburst patterns for engaging infantry, formations, dispersed fires for neutralizing vehicle concentrations, and mixed conventional, divided by proximity missions for engaging fortified positions. Forward observers received specialized training in target identification and engagement procedures that optimized proximity fuse deployment, while conserving the expensive munitions for situations where their advanced capabilities provided decisive advantages. Battery commanders learned to calculate ammunition mixes that balanced tactical effectiveness against logistical constraints, using conventional rounds for harassment and interdiction missions, while reserving VT fuses for critical defensive fires and counterattacks. The institutional learning curve was remarkable. American artillery units achieved full operational capability with proximity fuses within weeks of receiving the new technology, while German forces never developed effective countermeasures despite months of exposure to VT fuse bombardments. The organizational advantages that enabled rapid adaptation of advanced technology demonstrated systemic superiorities that extended far beyond individual weapons systems. As Christmas Day 1944 dawned cold and clear over the snow-covered Ardennes, German commanders confronting the systematic destruction of their offensive capabilities began to comprehend the magnitude of American technological superiority. The weather clearing that allowed Allied air power to resume operations revealed German formations that had been decimated not by aerial attack or tank battles, but by artillery systems that seemed to possess almost supernatural accuracy and effectiveness. Oberst Otto Skorzeny, commanding Special Forces operations during the northern thrust of the offensive, submitted reports documenting the psychological impact of American proximity fuse artillery on elite troops who had previously demonstrated exceptional battlefield resilience. American artillery has achieved a level of precision that affects soldier morale in ways that conventional bombardment cannot. Our most experienced assault troops report superstitious fear about shells that seem to know exactly when and where to explode for maximum effect. Unit commanders request permission to avoid areas subject to American artillery coverage, indicating a breakdown in offensive spirit that conventional weapons have never produced. The 6th SS Mountain Division Nord, transferred from Norway specifically for the Bulge offensive, suffered casualty rates exceeding 40% within the first week of operations, losses inflicted primarily by proximity fuse artillery rather than direct combat engagement. The mathematical progression had become undeniable. German forces were being systematically destroyed by weapons systems that rendered traditional infantry tactics obsolete while requiring no corresponding increase in American troop strength or conventional ammunition expenditure. The intelligence revelations emerging from captured German documents and prisoner interrogations provided definitive evidence that proximity fuses had achieved complete tactical surprise while demonstrating technological capabilities that German scientists couldn't explain or duplicate. Wehrmacht technical officers conducting field analysis of unexploded American shells reported findings to higher headquarters that revealed both the sophistication of VT fuse technology and the depth of German technological backwardness, electronics and miniaturization. Major Heinrich Weiss of the 352nd Infantry Division wrote in a report dated December 28, 1944, American proximity fuses represent technological advancement that exceeds our current understanding of battlefield electronics. Captured examples contain radio transmitters smaller than matchboxes that continue functioning after being fired from artillery pieces. Our technical personnel lack the equipment necessary to analyze these devices, and our industrial capacity could not duplicate such miniaturized electronics even if we possessed complete technical specifications. The Americans have achieved mass production of technology that we consider experimental laboratory equipment. German prisoners consistently reported that proximity fuse artillery produced casualties and psychological effects that exceeded anything experienced during years of fighting on multiple fronts, indicating that American forces had achieved qualitative advantages that compensated for initial tactical disadvantages during the Bulge offensive. The broader strategic implications of proximity fuse deployment transcended immediate battlefield effectiveness to demonstrate American advantages in the integration of scientific research, industrial production, and military application that would define post-war technological competition. The development timeline from initial concept to mass battlefield deployment had required exactly 24 months, a pace of innovation that reflected institutional capabilities for transforming theoretical research into practical weapons systems. The Johns Hopkins Applied Physics Laboratory, established specifically for proximity fuse development, demonstrated how American universities could contribute to military technology through research programs that maintained academic freedom while achieving practical results under wartime pressure. The manufacturing network that produced 1.2 million VT fuses by late 1944 represented industrial coordination across multiple sectors: electronics, precision manufacturing, chemical processing, and quality control that created technological capabilities extending far beyond individual weapons production. The systematic approach to problem solving, from initial physics research through mass production to battlefield deployment, established methodologies that would support American technological leadership in fields ranging from nuclear weapons to space exploration. German attempts to develop competing proximity fuse technology, initiated only after recognizing American capabilities during the Bulge fighting, never progressed beyond laboratory experimentation due to resource constraints and industrial limitations that reflected fundamental disadvantages in scientific infrastructure and manufacturing capability. The mathematical finality of German defeat became apparent through casualty statistics and unit effectiveness. Reports that documented the systematic degradation of offensive capabilities under proximity fuse bombardment. The 2nd Panzer Division, spearheading the drive toward Dinant on the Meuse River, suffered casualties exceeding 60% during the final week of December, 1,944 losses inflicted primarily by American artillery rather than tank-to-tank combat or infantry engagement. The division's combat effectiveness reports showed a direct correlation between proximity fuse artillery exposure and unit degradation. Companies subjected to intensive VT fuse bombardment lost offensive capability within 48 to 72 hours, regardless of initial troop strength or morale levels. The 26th Volksgrenadier Division, attacking American positions near Wiltz, reported that proximity fuse artillery could neutralize battalion-sized assault formations with battery-level fires that previously would have required division artillery to achieve comparable results. German medical statistics revealed wound patterns and casualty rates that exceeded anything recorded during previous campaigns, indicating that American artillery had achieved lethality levels that rendered traditional infantry assault tactics impossible. The strategic reserve formations that Hitler had committed to achieving breakthrough, including elite SS panzer divisions and veteran paratrooper units, were being systematically destroyed by weapon systems that most German soldiers couldn't understand and that German industry couldn't duplicate or counter. On New Year's Day 1945, as the German offensive ground to a halt amid the frozen forests of the Ardennes, the technological revolution represented by American proximity fuses had fundamentally altered the strategic balance of the European war. The failure of Wacht am Rhein, Hitler's last desperate gamble to reverse German fortunes, could be attributed directly to American technological superiority that compensated for initial tactical disadvantages through weapons systems that exceeded German comprehension or industrial capability. General Hasso von Manteuffel, commanding the 5th Panzer Army during the central thrust of the offensive, submitted after-action reports that acknowledged the decisive role of American proximity fuse artillery. Enemy defensive fires achieved effectiveness levels that rendered coordinated infantry assault impossible. Traditional tactics developed through years of successful operations have become obsolete against artillery systems that can engage attacking formations regardless of terrain, weather, or defensive measures. Our casualties from indirect fire exceed all previous experience, indicating fundamental changes in the nature of battlefield weapons. The Americans possess technological capabilities that we cannot match with current industrial resources. The statistical evidence was overwhelming. German forces had suffered approximately 100,000 casualties during the Bulge offensive, with proximity fuse artillery accounting for over 30,000 of those losses, demonstrating kill ratios that exceeded conventional artillery effectiveness by factors of 3 to 5 depending on tactical circumstances. The human testimony of German survivors provided the ultimate acknowledgement of American technological supremacy and the obsolescence of traditional military thinking in the face of electronic warfare. General Major Siegfried von Waldenberg, commanding the 116th Panzer Division during the drive toward the Meuse River, was captured on January 16, 1945, after his division had been destroyed by systematic American counterattacks supported by proximity fuse artillery. During interrogation by Allied intelligence officers, Waldenberg provided a statement that summarized the complete transformation of battlefield dynamics. "We entered this offensive confident in our tactical superiority and the proven effectiveness of German assault doctrine. We possessed initial advantages in troops, tanks, and surprise that should have ensured breakthrough against thinly held American positions. What we encountered was artillery that seemed to possess intelligence shells that exploded at exactly the right height and location to cause maximum casualties regardless of our defensive measures or tactical expertise. Our soldiers, veterans who had survived years of combat on multiple fronts, expressed genuine fear about American weapons that could reach them in any position or formation. The proximity fuse represents more than improved artillery. It demonstrates American technological capabilities that we cannot comprehend or counter. We were fighting with the weapons and tactics of 1940 against enemies who had advanced to forms of warfare that we did not know existed. The defeat was inevitable once we discovered that our fundamental assumptions about battlefield dynamics had become obsolete. The legacy of proximity fuse deployment during the Battle of the Bulge established precedents for technological warfare that would dominate military development throughout the Cold War and beyond. The successful integration of advanced electronics with conventional weapon systems demonstrated principles that would evolve into precision-guided munitions, smart bombs, and ultimately the networked battlefield systems that defined late 20th century military technology. The industrial processes developed for VT fuse mass production, miniaturized electronics, precision manufacturing, rigorous quality control, and systematic testing procedures became the foundation for post-war industries, ranging from consumer electronics to aerospace systems. The research methodologies that transformed theoretical physics into practical weapons within 24 months, established templates for technological development that supported American leadership in nuclear weapons, jet propulsion, radar systems, and eventually computer technology. The organizational capabilities that coordinated university research, industrial production, and military deployment created institutional advantages that enabled rapid innovation and deployment of advanced technologies throughout the post-war period. The proximity fuse represented more than a superior weapon. It embodied systemic advantages in science, industry, and military organization that established American technological dominance for generations. The strategic implications of American proximity fuse technology extended far beyond the immediate tactical victory at the Battle of the Bulge to demonstrate fundamental advantages in the relationship between scientific research, industrial capacity, and military effectiveness that would define the post-war international order. Nations worldwide recognized that American capabilities in advanced electronics and precision manufacturing represented technological leadership that could be applied across multiple domains from military weapons to civilian industry to space exploration. The Soviet Union, despite possessing overwhelming advantages in conventional military production, never achieved comparable capabilities in miniaturized electronics or precision-guided weapons throughout the Cold War period. European allies, including Britain with its advanced radar programs, and Germany with its theoretical research excellence, acknowledged that American industry possessed unique advantages in transforming laboratory discoveries into mass-produced battlefield systems. The proximity fuse demonstrated that technological superiority could compensate for numerical disadvantages while providing force multipliers that rendered traditional military calculations obsolete. The mathematical precision of American technological warfare, achieving 3 to 5 times greater effectiveness, while reducing ammunition consumption and personnel requirements, established paradigms for military efficiency that influenced defense planning and procurement policies for decades. In the end, the story of proximity fuses at the Battle of the Bulge represents more than military history. It constitutes a definitive demonstration of how scientific research, industrial capability, and systematic organization could combine to produce technological advantages that transcended traditional concepts of military power. The VT fuse wasn't just a better artillery fuse. It was a manifestation of American advantages in electronics, precision manufacturing, quality control, and systems integration that German industry couldn't match, despite possessing theoretical knowledge and traditional engineering excellence. The systematic destruction of German offensive capabilities during the Ardennes fighting demonstrated that technological superiority could compensate for tactical disadvantages, strategic surprise, and numerical inferiority through weapon systems that fundamentally altered the mathematics of combat effectiveness. The German surprise at facing proximity fuse artillery reflected more than tactical unpreparedness. It revealed the complete obsolescence of military thinking based on industrial age assumptions about weapons, tactics, and battlefield dynamics. American industry hadn't just built better artillery fuses, it had created the technological foundation for electronic warfare that would dominate military development for the remainder of the 20th century and beyond. The proximity fuse represented the future of warfare arriving on a World War II battlefield, demonstrating that democratic societies possessing advanced scientific infrastructure and sophisticated industrial capabilities could achieve military advantages that authoritarian alternatives couldn't comprehend, much less duplicate or counter. The lesson transcended military technology. When free societies mobilize their intellectual and industrial resources towards systematic innovation, the results exceed what centralized planning and traditional approaches can achieve, creating advantages so overwhelming that they render conventional resistance futile and establish new paradigms for human capability and technological achievement.